I am clear.
Okay, let's go ahead and get started. Let me just remind you of some of the policies associated with each lecture. There is a reading assignment, and you need to go into I'll put this in student view. For example, today is class 2. You would go into your schedule and you would click there, and that would give you an opportunity to tell us whether you read the reading assignment or you didn't, whether you get the 5 points or you don't. You would need to do that before midnight tonight, and then get your points. Your clicker points will be added to that to get your classroom participation score. You don't have a clicker, you need to get one right away. I've been watching on Facebook Marketplace, and I've seen them as cheap as $5 there, and so it's the cost of a hamburger. Okay. Why don't we start today with a prayer? Who would be willing to pray for us today? Any Latter-day Saints in the room? There we go.
Dear Father in heaven, we're thankful for the blessing that we have to be here in class. We're grateful for his hard work in teaching these classes and passion and kindness towards students, and we pray that we can have our hearts and minds open today with that. May have opportunity to hear place, and that we may perform well in this class. We're thankful to be here once again.
Thank you. I've shared this with most of you before, but I was sent to you. I was offered the job here, and my wife and I talked about it and decided that that was the last thing we wanted to do, that we were happy in Bozeman, Montana. We loved our friends, our neighbors, the beautiful mountains around us, and there was no way we were going to leave. And then we thought, well, maybe, just maybe, we should ask the Lord about that. And so we went to the temple in Helena and asked the Lord. And at that point, we were stuck. And I've got to tell you, I brought my dear wife here kicking and screaming. But we have come to love it, and I have come to realize that I'm not here doing the Lord a favor or doing you a favor. Over the last year and a half, I've come to realize that I was the one that needed this. I was the one that needed to be exposed to your wonderful spirits, that just the energy I get from your wholesomeness and your cheerfulness. It's really changed my life. So thank you to you. I appreciate you. We're going to start today the way we sometimes start, and that's with a, come on, there we go, with a clicker question. Taking roll. Okay, now you can click.
I wish it was like here that it's actually
Like if it's not there right now, I'd say about.
When you turn on one of these clickers, these iClicker 2s, it will come up with the channel, and it should read the channel AA. That's what the base is set to, is channel AA. Okay, last call, get your vote in. Okay. We are mostly here. Okay. If we could, have a really quick review of where we were at the end of last class. We were talking about what charge was, and we decided it was just a property of an object. And we talked about an object that might have a color that I call blue, a shape that I call round, a mass that I measure to be 2 kilograms, and a charge that I measure to be -3 microcoulomb. And that -3 microcoulomb just tells me I've got extra electrons on there. And it tells me how many extra electrons I have on there. Now, because it has mass, it can exert a gravitational force on other things with mass. And because it has charge, it can exert an electrical force on other things that have charge. Now, when we were talking about gravity back in 105, it was this universal law of gravity that Newton gave us that governed that force. And the striking thing about it, well, two striking things. First of all, it depends on the product of those masses. They're multiplied. And that tells me that Newton's third law is built right into the law of gravity. Because 3 times 4 is equal to 4 times 3. It's just built right in. The second thing we notice is that it's 1 over r squared. And what that means is that if I move these two objects twice as far apart, the force between them gets 1/4 as big. 3 times as far is 1/9 as big. 4 times as far, 1/16 as big. So this very quickly falls off with distance. Okay. Now that constant, it took 100 years to measure that constant. Henry Cavendish was the one who did it 100 years after Newton gave us that law. And it's a very, very tiny number. But essentially, what I would have to do to get that number is simple in principle. I would just take a 1 kilogram mass and put it 1 meter away from another 1 kilogram mass and measure how hard they were pulling on each other. And if that's 1 and that's 1 and that's 1 squared, then the force that I measure is going to be that constant, and it would be the same constant throughout the universe and throughout all time, we think. Okay? Now, that force is always attractive. There's only one flavor of mass, positive mass, and it always attracts other mass. Now, it doesn't matter, again, whether one of those masses is huge and the other is small. The forces on each other are equal and opposite by what law? By Newton's third law. By Newton's third law. Okay, and it's built right into the equation. Now, we talked about this electric force, Coulomb's law, and we noticed that it was very, very similar to our gravitational force. Instead of masses, we have charges, Q1 and Q2. But it still depends on a 1 over r squared relationship. And if these two are both positive, then I'm going to get a repulsive force. If they're both negative, I'm going to get a repulsive force. But if one is positive and one is negative, I get an attractive force. Now that constant of proportionality I gave you last day, I'll put it on the board again. It will be on the front page of your midterm. It's really easy to remember. It's 9 times 10 to the 9th Newton meters squared over Coulomb squared. Okay. Now, the difference between mass and charge is that mass only comes in one flavor and charge comes in 2. And what that means is that when I have a spherical object, Newton created the calculus to prove that we could take all of the mass of the spherical Earth and pretend it was right there at the center of the Earth, and we would get the right answer, okay? But that's because the mass is distributed in a spherically symmetric way. Now, we saw with a neutral can that if I brought a charged rod up to it, the right side of the can got charged with positive, and the left-hand side got charged up with negative charge. And suddenly the symmetry went away. And so what we know about the gravitational force isn't always true for the electric force. Indeed, we know that if Q2 is equal to 0, this equation's not always going to work. Okay? If I plug in 0 for Q2, it tells me there's no force. But yet that can that had Q0 felt a force. And that's because this equation, Coulomb's law, has caution tape around it, yellow caution tape, danger, danger. Don't even think of using that equation unless you're dealing with small objects, okay? Because if this object is small compared to this distance here, then the left side of this little tiny object is going to be the same distance from this, pretty much, as the right side of that object. Okay, and so I'm not going to get that charge separation that allowed the neutral objects to be attracted to charged objects. See if your neighbor understands that difference between the electric force and the gravitational force. Talk to your neighbor, people. Wake up. Okay. Who is that? Miriam, who is that? What's his middle name? That's his middle initial. Very good. What does the T stand for? A geek right there.
It's Tiberius.
Tiberius, yes, geek. And I say that with love. Those are good people, geeks, okay? James Tiberius Kirk. And he was the captain in the original Star Trek, the Star Trek that I grew up with. And back in those days, they had amazing technology. They had a thing that they could flip open and talk to people far away. They had doors that would just open up whenever you came towards them. This blew our minds because we were simple folk, okay? Now, they also had a very, very restricted budget. And going to another planet and creating, you know, all the different culture on another planet was expensive. They didn't have the green screen technology and computer-aided cinematography like we have now. And so they had to do it on the cheap. And so what they did often is they'd get to that planet, or they'd be going down to the planet, and Spock would say, oh, the surface does not support life. All of their civilization is in tunnels underneath the ground. And so once again, we found James T. Kirk and Captain Spock and a bunch of guys in red shirts running through tunnels. And James T. Kirk was always out in front because he was an alpha male. And every now and again, he would run in to a force field, pow, and be thrown on his keister. Now, that's what we're going to talk about today, is the idea of a field. And I just wanted you to recognize that you've been exposed to this idea before. And I want you to remember three things about that field that threw Captain Kirk on his keister. One, that field was invisible. He didn't see it or he wouldn't have run into it. Two, Captain Kirk did not make the field. It was made by Klingons when they were the bad guys before they joined the Federation, okay? And three, there was no force on Captain Kirk until he was in the field. And then the field put the force on Captain Kirk. Remember those three things, they're going to be vital when we talk about the electric field. But before we talk about the electric field, let's talk about a field that you were exposed to, sort of, in 105, the gravitational field. You remember that when we were trying to find the force between the Earth and a book, one way to do it was to just take the mass of that book and multiply it by this number that we measured, 9.8 newtons for each kilogram, okay? If I had 1 kilogram, the Earth was going to pull on that with 9.8 newtons. If I had 2 kilograms, it was going to pull on it with a number that was hard to figure. So we made that number 10, didn't we? Yeah, we did. We wrote that as 10 most of the time. But you remember that the real formula for that gravitational force was given to us by Newton, and it had that form up in the upper right-hand corner. And if I use that, I have to know the distance between the book and the center of the Earth. Well, that was a number that was easy to measure. I was able to do that with my high school students in a high school teachers, I should say, using just a meter stick and a pond and Mount Rainier. Okay, it turns out that Henry Cavendish gave us the mass of the Earth. And so when we plug into that formula up there, it looks like that. Now, there's the mass of the book. That means that everything else, everything in that red box, has to multiply and divide out to 9.8 newtons for each kilogram. And that's what we call the gravitational field strength on the surface of the Earth. That's how hard the Earth pulls on every 1 kilogram of mass. Now, that's if we are very close to the surface of the Earth. Now, if I take 1 kilogram and put it close to the surface, I'm going to get a force of 9.8, let's call it 10 newtons, and it would be towards the center of the Earth, okay? A little bit further out, quite a bit further out, I might put that 1 kilogram block and measure it to be 5 newtons. And somewhere in between, I might measure it to be 7 newtons. Now, what if I don't put a 1 kilogram block there? What if I put a 3 kilogram block there? What's the force going to be? Quickly tell your neighbor. Yeah, it's that easy, okay? It's going to be 5 newtons for each kilogram. I got 3 of them. And so I'm going to have a force of 15 newtons. Now, what I want you to notice is that there are 2 vectors. There's one vector, the blue vector. We call that the gravitational field. And that's got waffle words in it. That's the force that the Earth would exert if I put 1 kilogram there. But I didn't. I didn't put 1 kilogram there. I put 3 kilograms there. So the red vector is what force actually acts on the object that I actually put at that location. You can think of this blue vector as a rate, kind of like the price of a gallon of gas. You know, you could imagine a world where we didn't have the price of a gallon of gas, where you drive in with your car and you ask, how much is it going to cost to fill it up? And they ask, well, what kind of car do you have? How big's your tank? How empty are you? I'll look it up in the tables. No, if you know that the gas is $3 a gallon and I need 10 gallons, $30. It's that easy, okay? The blue vector is the rate, how much force there is for 1 unit of mass, and that's the actual force for how many units I put there. I know it sounds simple because it is. Okay, but a lot of people, when they first encounter the idea of field, get a little confused. Now, the gravitational field strength at that location is the 5 newtons for each kilogram. So here's another question. Suppose I put 5 kilograms at this location and I measured the gravitational force to be 35 newtons. What's the gravitational field strength there? Tell your neighbor real quick. Okay, it's that easy. It's 7 newtons for each kilogram. If I put a 1 kilogram block there, it would feel a force of 7 newtons, but I didn't. I put 5 kilograms there, so it's 5 times 7 or 35. Now, the gravitational field of the Earth is very, very simple. It always points towards the center of the Earth, and it gets weaker as I go further away from the center of the Earth. But to find the actual force, I just take the gravitational field strength that we always use a little g to indicate. And again, that's the rate. That's how much force I would have for 1 unit of mass. And then I multiply by how many units I have. Now, that gravitational field is deadly boring. That's why we didn't really talk about it last semester or whenever you took 105. If we had magical glasses that could see that gravitational field in this room, every point in the room would have a vector pointing straight down, and the vectors would all be the same length. They'd all be 9.8 newtons per kilogram. Okay, boring, boring. But we're going to talk about a more exciting field, the electric field. And it's defined by this equation. That's the operational definition. Now, I say it's more interesting because it's not the same everywhere in the room. The gravitational field is caused by mass. The electric field is caused by charge. And suppose this iPad is positive, and suppose this that's a MacBook. No, MacBook is negative, and that's positive. The field in this room, that would be the blue vector, can be very, very different from point to point. Over here, it could be pointing this way. Over here, it could be pointing that way. Over here, it could be pointing this way. It could be really, really strong right here. It could be really, really weak over there. Indeed, if we had those magic glasses that could see this everywhere, we'd go crazy. It'd just be so complex, so complex. Now, suppose I were to tell you that the electric field, due to all of these things that are charged, that the electric field right here at this location pointed that direction and had magnitude 5. I left off the units on purpose. What does that 5 tell you about this location of space? Talk to your neighbor. What does that 5 tell you about that location? Okay. Just like the gravitational field had waffle words, so does the electric field. If that electric field right there is 5 and pointing that direction, what that says is that if I were to reach into my pocket and if I were to pull out 1 Coulomb of charge, killing us all, okay, and if I were to put that 1 Coulomb at that location, it would feel a force of 5 newtons that direction. Did you hear all the waffle words? Okay. Now, the electric field is the force that positive 1 Coulomb would feel if it were placed at that location. Now, that's why the electric field is valuable. Because if I know what the force is for 1 coulomb, I know what the force is for 2 coulombs or 3 coulombs or 10 coulombs, or indeed 1 nanocoulomb. All I have to do is take the electric field, the force on 1 coulomb, and scale it, multiply it by how many coulombs I actually put there, just like we did with the gravitational field. Does that make sense? Are there questions? Now, this is important. That electric field is not created by this charge in the equation, okay? This charge here is the Captain Kirk, okay? That charge there, we sometimes call it the test charge, is the charge that's being pushed, the charge that's being thrown on his keister. That's the Captain Kirk. This electric field is being created by all the other charges, the Klingons, okay, that are creating the field. We'll talk about that in a minute. Now, the units should be obvious. If the force is in newtons and Q is in coulombs, then in order to make the units the same on both sides of the equal sign, I've got to have units of newtons per coulomb, but we're never going to say it that way. We're going to pronounce it newtons for each coulomb that I put at that location. Newtons for each coulomb that I put at that location. Now, I've got some examples to help us understand what's going on here. Example number 1. At the location marked with an X, the electric field is 2,000 newtons for each coulomb and points to the right. What is the electric force, size, and direction on a 6 microcoulomb, 6 times 10 to the minus 6 coulombs, charge that is placed at the X? Well, we're told the electric field is to the right, and we're told how big it is, and we're told that we're putting a positive charge there, okay? So if I put the operational definition up here. Whoa, not with that one. That one I'm donating to the room. Okay. The electric force is equal to Q. We'll call that Q test times the electric field. If this is to the right and the test charge is positive, then the force is going to be in the positive right direction. And I can find easily its magnitude. Remember, a magnitude is always a positive number. Always, always, always. When? Always, every stinking time, okay? I just multiply the charge times the 2,000, that's the electric field, and I get this force there. Now, this is where things get a little bit different than the gravitational case. I can also, before I go there, it's been my experience that when we're dealing with electric fields and forces, we're dealing with a lot of very large numbers and a lot of very small numbers. You saw that in your homework. You've got that exponential in there all the time, 10 to the minus 9, 10 to the minus 19, over and over again. I find that there's something I call Lee's law of large numbers. And that is when you get these numbers with the 10 to the something, your mind just kind of fades out. So let's revisit this with some numbers that you can do in your head. Suppose the field was 20 newtons for each coulomb, and we put 3 coulombs there. You could do that in your head. There's 3 newtons of force for each of the coulombs, and I got 3 of them. I would now have 60 newtons to the right. Does that speak to your soul? Okay, good. Now, what if the charge were the same size, but negative? What if I put a negative 6 times 10 to the minus 6. Well, the electric field is still to the right. The charge is negative, and that means the direction is going to be in the negative right direction. Do we have another name for that, negative right? Yeah, let's call it left. Okay, that's left. And so in this case, I'm going to have the same magnitude, always a positive number, but it's going to point to the left. And if I use those revised numbers, it would be 60 newtons to the left. Does that make sense? Everyone on the bus? No one left behind? Okay. What if I put that charge over here? What would the force be? I don't know. That's the thing about the electric field. It can change from point to point fairly drastically. I have no idea what the field is here. I was told what the field was there. So the answer is, we don't know. We don't know. Okay. Now, here's an example 2. I have a negative charge, negative 5 times 10 to the minus 8 coulombs, negative 50 nanocoulombs, and it feels a force of 0.2 newtons to the right. What is the electric field, magnitude, and direction at the charge's location? Well, first of all, the direction. If it's a negative test charge, a negative Captain Kirk, what direction does the field have to point in order for the force to be to the right? Has to be to the left, okay? So, oops, wrong button, to the left. Now the size we can get just from the operational definition of the electric field. If the force is 0.2 and the charge is negative 5 times 10 to the negative 8, I just divide both sides by the charge and I get 4 million newtons for each coulomb. And it's to the left. Okay. Now, notice that when I was doing this number here, I didn't get a negative number here. Well, I did, but I incorporated it into the right. If I had done that step by step, what I would have said was the electric field was equal to the force divided by the charge, the test charge, and this was 0.2 newtons to the right, and I would divide that by negative 5 times 10 to the minus 8 coulombs, and then I want the magnitude, and that's a positive number, and that's going to be my 4 times 10 to the 6 newtons per coulomb. And then I take everything that's left over, and that's going to be negative right. And that gives me my direction, which is left. Okay. A question was asked before class started. When do we ignore minus signs? And the answer is never. But sometimes we just kind of take care of them in our head, okay? Because we know it's going to turn out to be left, and we know we want a magnitude that's positive. We just, you know, get rid of that and just use our gut to say it's left. That makes sense? Okay. Now, let's revisit that with some numbers that speak to our soul. Suppose the charge is negative 5 coulombs. Again, not worrying about the fact that it's killing us all. And the force that it feels is 15 newtons. Well, if 5 coulombs feels a force of 15 newtons, then that means each 1 coulomb is going to feel a force of 3 newtons. 3 newtons for each 1 coulomb times 5 gives me the 15. Okay, that's something you can do in your head. Now, where does the E come from? What creates the field? Well, This force in the equation is the force on this charge, the test charge, the Captain Kirk, okay? And that E field is due to all the other charges, we call them source charges, in the universe. Now, because this Coulomb's law falls off with 1 over r squared, we don't really need to take all of the charges in the universe. Indeed, once you get a couple of meters away, you know, this force has fallen off pretty quickly. And so it's just the other charges that are nearby that are pushing on the test charge. We call them the Klingons, okay? The Klingons. Now, how big? Well, first of all, let's talk about direction. If I have a positive Klingon here, a positive source charge, what direction is going to be the field at the X? Shout it out all together. And a great and mighty shout went up in the land. Again, to the right, okay? Away from the positive Klingon, away from the source. If I have a negative Klingon, a negative source, the field is going to be to the left or towards the negative source, okay? Always away from a positive, always towards a negative. Always, 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 okay? But how big? Well, for a point charge, it looks like that. And I'm going to put that on the board. Does someone see my black marker? Wow, that's just unfortunate. Okay, we're going to put that right up here. Isn't it funny when old people get lost? Oh. Now notice I use a capital Q instead of a little q. Does that change everything? Does that just ruin our day? No, sometimes we use a capital Q, sometimes a little q. Deal with it, okay? Deal with it. Now, if I remind myself that k is equal to 9 times 10 to the 9, and I use this last example, I have a 2.5 microcoulomb charge, a source charge, and it's glued to the sky right there. It's locked in place right there. And we always assume that our sources are fixed in place, because if our sources start running around the room, that makes the problem very, very tricky, okay? So we always glue them to the table or staple them to the sky. We want to find the electric field at a point that's 5 centimeters to the right. Well, if I plug into this equation, there's my K, there's my test charge, or my source charge, there's my Klingon, and then I've got to convert my 5 centimeters into meters, always meters, and I've got to remember to square it. A lot of you on the exam will forget to hit that square button. Turn to your neighbor and say, that will be you, not me.
No, it's gonna be me. No, based on my track.
Now, when I do the math, I get 9 million newtons for each coulomb with a positive sign out there. And what does that positive sign tell me? Shout it out. Right? 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 Are you sure? You feel that strongly in your bones? Okay. Well, yeah, points to the right. But what if I had told you that the X was over here? Then I would have plugged in a -5 times 10 to the -2 meters there. but I'm squaring it. So what does that tell me? I'm still gonna get this answer. Okay, and now what does that plus sign mean? Left. Okay, well, that's confusing. Sometimes it means right, sometimes it means left. No, it always means away. Okay, if I got a positive source, this is a positive number, this is always positive. So a positive source, the positive number for E is gonna mean away. And a negative number for E is gonna be towards, okay? Try to keep that in your toolbox. Now, it turns out that calling one direction positive is crazy talk in 3 dimensions. If I call this the positive x-axis, well, there's an infinite number of other directions that I can point. Which one am I gonna choose to be my negative axis? And then what do I call the others? That one's Fred, that one's Sally, that one's, okay? And that's why when we're dealing in 3 dimensions, we always look for the magnitude of the electric field. We look for the magnitude of the electric field by taking the absolute value of my source charge, my Klingon, and then we use our gut to find the direction. Again, away from a positive Klingon towards a negative Klingon. Now, that begs the question, how do I recognize which charge is the Klingon and which charge is the Captain Kirk? Which charge is creating the field and which charge is experiencing the field? In other words, how do I recognize a Klingon? Well, that's what they look like. Okay, that's how you recognize them. Now, I have for your enjoyment a worksheet, and if I could get some help handing these out, thank you. If you'd start in the back, and you'll start in the front, and I'll start in the middle. Okay. Now, there's physics on both sides. Just pass it down quickly. Don't be reading it before you pass it. You guys not kidding me? Oh, man. That's criminal. Thank you. Save these for all those lesser students in the later class. Thank you. Hey folks, speaking of the later class, the 3:30 class has a room that's only half full. Plenty of room to spread out. You can tap dance, whatever you want to do. So if you have room in your schedule at 3:30 in the afternoon, feel free to go to that class. Remember, regardless of which of the 3 lectures you go to during a day, if you use your clicker in any one of those 3, you get credit for attending that day. Okay? Now, what we see in this handout is that there are 2 charges. Q1 is 3 nanocoulomb, and Q2 is a negative 6 nanocoulombs. And they are separated by a distance of 20 centimeters. Now, the first question you're asked is, what is the electric field strength at the location of Q1 due to Q2? Now, remember, my formula here has absolute value here and here, because we're looking for the magnitude. What we're trying to figure out here is which one is the Klingon creating the field and which one is the Captain Kirk that's experiencing the field. Talk to your neighbor, which one do we care about when we're trying to figure out how big the electric field is? Find the Klingon. Is it Q1 or is it Q2? Talk to your neighbor. Okay. I hope it's clear from the wording that if I were to take Q1 and I were to replace it with an elephant, does that change the problem? If I were to ask you, what is the electric field strength at the location of the elephant due to Q2, would I get the same answer? Yeah. At the location of Q1, that's an address. That's like a mailbox, okay? And so what we care about is Q2, and we can see that due to the because of the wording, due to Q2. That tells me that Q2 is the one creating the field. Oh, that's the Klingon. That's the Klingon. So I replace Q1 with empty space, or maybe I put a little X there, and I ask myself, what kind of electric field am I going to get at that X? First of all, the direction, is it going to point away from Q2 or towards Q2? Towards, it's a negative Klingon, a negative source. And so I'm going to get an electric field towards the negative source. And I would use that operational definition on the board to figure out how big it is. Notice that I didn't put the minus sign in here because I'm just looking for the magnitude, just the magnitude, okay? And when I plug in those numbers, again, remembering to square the 0.2 meters in the basement, I get 1,350 newtons for each Coulomb. Okay? A number that we don't care strongly about, but it's part of the exercise. So let's label that like that. Are there questions here? Because this is a crucial fork in the road. Okay, here we understand it or we don't understand it. Okay. Now, if I want to know what force Q1 experiences, well, Q2 has already done its job. It set up the field, okay? The Klingon set up the field in that tunnel and went back to the home planet, leaving the field behind for Captain Kirk to run into, okay? So we don't have to worry about the Klingon anymore, okay? And we put that Q1 back at the location of the field, and because it's a positive Captain Kirk, a positive test charge, the force is going to be in the same direction as the field. And now I just use the operational definition of the electric field. I take the electric field of 1,350 newtons for each Coulomb, and I've got 3 nanocoulombs. And so when I multiply that together, I get 4 micronewtons, or 4 times 10 to the minus 6 newtons to the right. Quickly check on your neighbor. See if your neighbor is fully comprehending what we're doing here. Do a buddy check.
Trying to figure out. Get rid of that. Just do what you say, because. Well.
Okay,
The electric field. In the equation.
question in the back here. The field, the blue vector is away from a positive source and towards a negative source. Okay, but the red vector, that's the force. And that is governed by this equation that would be oh so much better. There's my black one. If the field is to the right and the test charge is positive, then the force is in the positive right direction. Okay. Now, let's try it again. What is the electric field strength at the location of Q2 due to Q1? Again, which one's the Klingon, which one's Captain Kirk? Well, the key there is due to Q1. And I can also ask, how does this change the problem? If I were to put an elephant at the location of Q2, the electric field at that location is totally independent of whether it's an elephant there, or whether it's a mailbox there, or whether it's Q2 there. Totally independent. It only depends on the Klingon, which in this case is Q1. Now remember, Q1 used to be Captain Kirk, but now we're asking a different question, okay? We're asking about the force that's going to be acting on Q2, so we need Q1 to set up the field. Now, what I do is I replace Q2 with a location marker, and then I ask, if this is a positive source, what direction is the field going to be over here? And this is where we use away from a positive source, and so it's going to be to the right. And the size is going to be given by this Coulomb's law. I put in my K value. The 3 nanocoulombs was positive, so I didn't need to ignore anything there. And I divide by the distance, and I get 675 newtons for each coulomb. Okay. Now, if I want to know what force Q2 experiences, well, now Q1 has done its job. The Klingon has set up the field, gone back to the home planet. I can get rid of it. And now I just ask, if I put a negative test charge at that location, well, now my field is to the right, my test charge is negative, so my direction of my force is going to be in the negative right direction or left. And if I use the operational definition of the electric field, again, I left off the minus sign because I know it's to the left, okay? And so I get 4 times 10 to the minus 6 newtons for newtons, full stop. Okay, let me just review where we've been. We found that the field due to Q2 was 1,350 newtons per kilogram. Did I say per kilogram? I did not. If you say that I did, I'll call you liars. Okay, who are they going to believe, me or all of you? Newtons for each Coulomb to the right, and the one due to Q1 over there is 675 newtons for each Coulomb to the right. And these fields are equal and opposite by what law? Shout it out. Oh, for crying out loud, people, they're not equal. They're not opposite. Bazinga. I gotcha. There is no Newton's third law for fields. Newton's third law applies to forces. The actual red vector that actually pushes and tugs and pulls on actual objects. The blue vector, the field, is a gimmick. It's a way of getting what we really care about, the force. Now here's a little bit of history. In the beginning, physicists were kind of disturbed by the fact that a charge here could push on a charge back there at the back of the room through empty space. That seemed spooky. And so it seemed useful to them to think of this charge up here changing the room, setting up this field, this imaginary thing throughout the room. And then the field could do the pushing. It seemed so convenient and yet so hokey. And yet later we find that this field is a real life thing. Okay, what you see when you see light coming out of that fixture there is an electromagnetic wave where you've got an electric field and a magnetic field that are oscillating, creating each other. We'll learn about that a little bit down the road. It turned out to be real. And so we have to treat it with respect, okay? But we don't have a third law for the field. What we have is a third law for forces. We found that the force on Q2 was 4 micronewtons to the left, and the force on Q1 was 4 micronewtons to the right. And those are equal and opposite by third law. By third law. Okay? And if I were to label those the way we did in 105, this would be the force by 2 on 1, and this would be the force by 1 on 2. And they're both electrical forces. And when you find that you have the same flavor of force with the indices reversed, that was how you recognize third law force pairs that have to always be the same magnitude, but opposite directions. Now, we're going to do something a little bit different, something exciting. Going to turn up the lights here. What I have here are 2 plates, metal plates, and they're separated by a non-conductor. And we just have a little bit of fishing wire here to keep this metallic ball. It's actually a ping pong ball with metallic paint inside the cage. And Clark, did you set this up, or was it in the department before your time? Okay, sometime around Adam. Okay, yeah. Okay. So we're going to hook the plates to different parts of this Van de Graaff generator. Now, the Van de Graaff generator is a really, really simple device if you understand what's going on. It's got a big rubber band inside, and when I turn it on, that rubber band rolls on a couple of rollers, okay? Now, there's 2 other important parts, and they look like this comb here, but they're made out of metal. And we're going to learn next week that near a sharp point, we get very, very strong electric fields. And so down in this box here, there's a metal comb, and that comb with its strong electric field is going to throw electrons onto this rubber band. Now, is that rubber a conductor or a non-conductor? It's a non-conductor. And so that means that when that electron hits the rubber band, it's stuck. It can't just go to its happy place. It's stuck wherever it landed. And then the rubber band rolls on the rollers, bringing that electron up into this metal ball. Now inside this ball, there's another metal cone, and it has strong electric fields that drag the electron off of the rubber band and put it on the inside of that metal ball. Now, pretty soon I get a bunch of electrons on that metal ball. Do they want to be next to each other? No, they want to spread out. They want to get to the outside of that metal ball. And they find that they can even spread out more if they go down this metal cable onto this plate here. Okay, so once I turn this on, I'm going to be dumping a bunch of electrons onto this plate right here on top. Now, where do those electrons come from? Is there an electron store in here that I'm buying them from? No, this thing is dragging electrons off of the bottom plate through this wire and shooting them onto this rubber band. So what the Van de Graaff is doing is it's robbing electrons from the bottom plate, putting them on the top plate. Okay, everyone clear on that? Now, let's forget about that for a moment. Suppose I were to take some charged paint that I got down at Lowe's, and this is positively charged paint, and I paint the floor with that paint. What direction is the electric field right here in the middle of the room going to point? With your finger, point the direction that the electric field would point. Up. Okay. Now, suppose you go back to Lowe's and you get a whole bunch of negatively charged paint and you paint the ceiling. Forget about the floor. Just concentrate on the ceiling, the negative paint on the ceiling. What direction would the electric field here be due to that ceiling? With your finger. Up. Okay, so I would have an electric field in this room that's partially up due to the floor and partially up due to the ceiling. Is that right? But we agree that when I add those two together, I get something up. Okay, now that means that once I charge this plate up negatively and this plate positively, this is like the floor and this is like the ceiling, I'm going to have a field in there that's up. Well, let's see what happens here. Now, back in Montana, I would drop it in, but there's no space to get that in there, so I'm just gonna. I would ask you, is that a perpetual motion machine? No, that's going to keep going as long as I keep replenishing. As long as I keep the rubber band going, as long as I keep moving charged electrons from the bottom to the top, it'll keep going forever. But that's requiring energy over here. I have a neighbor who's a patent attorney, and he always gets these people coming in and saying they've got a perpetual motion machine. He says, okay, set one up and let's watch it go forever, and then I'll put your patent in. Okay, now let's figure out why that did what it did. When that metal ball hits the positive bottom plate, it becomes charged. Okay, what charge does it acquire? Positive or negative? If it's metal and it hits a positively charged plate, some of the positive charge is going to go on that metal ball. Now, a positive Captain Kirk, a positive test charge in a field up is going to be pushed up. Replace right with up, and you're going to get up. Okay. Then that metal ball hits the roof, which is negative, and takes on some of the negative charge. Now that negative charge in a field that's still up is going to be pushed what direction? Down, the negative up direction, okay? And then it hits the floor again and becomes positive. Now it feels a force up, then it hits the ceiling and becomes negative, and it feels a force down, up and down, up and down, up and down. Now, when I turned off the rubber band, each time the ball made a trip, it brought some of the electrons on the ceiling back down to the floor. And so each trip that it made, it was essentially neutralizing the plates. Okay, it was moving the electrons back to where they started out on the floor. See if your neighbor understood that demo, please. We want you to understand that demo.
What I don't understand is that when he said, bottom electron at the top of the negative, right? So it's gonna be less electrons on the bottom, but it's more on the top. So it takes a lot of, is it that transferring electrons from the ball to the plate down the wire back up to the ball? Now it's gonna be wiring electrons.
If we go back to the idea of the field, the blue vector, and the force, the red vector, the field between those two plates is always up. It doesn't change during this whole demo. It's always up. But the force was up when the ball was charged positively, and it was down when the ball was charged negatively. And so the force, the thing that's actually doing the pushing, was changing up to down, up to down, up to down. But the field stayed up. That was the one with the waffle word. That would be the force that would act if I actually put +1 Coulomb in there. It would be up. Okay? Now, let's see, there we go. Part E. What is the electric field at the midpoint between the charges? Now who's the Klingon? Okay, talk to your neighbor. Who's the Klingon now? Okay. I've got two Klingons. Okay. The field at the center between those two charges is going to be partially due to Q1 and partially due to Q2. But if I look at my equation, Coulomb's law, for the electric field, I only have room for one Q. So what do? Do I average them? What do I do? What I do is exactly the same thing that I did in 105 when we had more than one pulse on a string or a spring or a rope. We use superposition. We added them up, okay? And so what we do is we take the charges one at a time. First of all, I pretend that Q1 is the only Klingon in the problem. And I ask myself, if Q2 did not exist, what field would I have just due to Q1 at that X? Okay. And then I ask myself, well, what contribution would I get from Q2 if Q1 didn't exist and Q2 were the only Klingon in the problem? What field would I get due to Q2? And you see that this one is away from the positive and this one is towards the negative, but they both point to the right. And so the total field is going to be the sum, the vector sum of the two fields. Now, if I do the math, okay, when I find the field due to Q1, I plug in my 3 nanocoulombs. And notice I've changed the basement. This used to be 20 centimeters and now it's 10 centimeters because it's always the distance from the source, the Klingon, to where the field is being created. And that's now 10 centimeters not 20 centimeters. Now that gives me a number that is 2,700 newtons for each Coulomb. If I do the same thing over here, I would expect a number twice as big because my source charge is twice as big and the distance to the X is the same. Okay, and sure enough, I get something twice as big. And when I add those together, I get 8,100 newtons for each Coulomb. Okay. So if you have more than one source, what you do is you break up the problem into parts and solve each part separately, and then add the solutions back together. Now, what if I were to take a third charge that was -2 microcoulombs and put it at that location? Again, the sources are glued to the sky, glued to the table, however you want to be thinking about this. What direction would the force point? Would it be left or right? The negative test charge, the total field is to the right. The force would be left. Okay. And I could find out how big it was just by multiplying the charge by the field, and I get 0.016 newtons. Okay. Now, with your clicker, I'm going to have one more clicker question here. Suppose that I have two identical positive charges, one at A and one at B. They're exactly the same size charge, and at at C, I want to know the direction of the electric field due to these two sources, these two Klingons. First of all, what's at the X? Garnets, absolutely nothing. Empty space. It's just a placeholder, okay? But I pretend that I pull out a 1 Coulomb and put it there, and I ask myself, how would 1 Coulomb be pushed if I put 1 Coulomb there? Now, with your clicker, before we go to devotional, now you can click. Okay, get her done. You get credit whether you get it right or wrong. Last call. Scramble, scramble, scramble. Good job, people, good job. If I look at the charge at B, I'm going to get a field that's away from the positive source. I'm also going to get something away from the positive source at A, but since it's twice as far away, it would be 1/4 as strong. And so when I add those two together, I would get C. Okay, President Reese and his lovely wife are going to be speaking to us at the devotional today. Go get a good seat.
Yeah.
That was a trip. Yeah. One bus would come on, and I jumped back on. Yeah. And I always drag it.